Year's lecture this year, and it seems we're having a new routine emerging here with this seminar room without tables. It's probably a good idea to first get jump on the food and eat a little bit, and then start like around 1/4 instead of at 12 directly. Thanks very much to Alessandro, who has stepped in on quite short notice to give this talk today on the connection between general relativity and quantum mechanics. So, the floor is yours.
Thank you for giving me the opportunity to start in. So, since now, so I try to make a talk which is in the spirit of this kind of seminar, which is very divulgative and open to people who are doesn't have a physical background. So I basically try to tell a story, and in fact this is like the title I gave before understanding this, because I just got a short notice. And then I decided to make something a little more divulgative. And so I decided to try to tell a story, okay? Because it's much more interesting, especially when somebody's eating. So I will speak about two forces of the four forces we have in nature, and that here at CP3 we are studying. As you know, there is gravity, and then there is the electromagnetic force, and then there are other two subatomic forces, the weak force and the strong force. Okay? In this talk, I will mainly speak about these two forces, Coulomb's law and electromagnetism and gravity. So I will start really from the beginning, because I really want to try to tell a story starting, for example, here at the beginning of the 19th century, when people was for the first time starting to study how charges interact and create fields. Okay? So at that time, people knew that there were some charges, okay? And people knew that these charges were creating a kind of field in space. Okay? That afterwards was called the electromagnetic field. So here the electromagnetic field will always be denoted with a green color. Okay? I try not to use equation as far as I can. So I try to make a kind of infographics for telling the physics behind electromagnetism and after gravity. And there is a very interesting law, which was the law discovered by Coulomb. This was, you see, already in the 18th century, at the time of the French Revolution, basically, when in French people was very illuminated and they were really doing a lot of science. So basically, they understood that there is an interaction. Oh, sorry, you cannot see the color. That's the problem. So there is a gray color in the slides. So basically, so the law which describes the electric field generated by a charge that I put it there. It's a very simple law, and it can be stated graphically or infographically in a very simple way, because it tells you that basically an electric field always has a source, okay? And Gauss law just tells you that if you just surround this charge by a surface of any kind, of any shape, and you calculate how much electric field is coming up from there, this is a fixed quantity, and the fixed quantity is the total charge that you have inside, okay? So for example, this can be used very easily to find out that restate the law that Coulomb found at that time. So basically, this is my electric field that I draw like this, okay? The electric field by symmetry will point outwards. And what I know is that I just have to multiply the value of the electric field for the surface that I have here. And this is what I'm doing here. So I find 4 pi r squared is like the surface of the sphere, okay? And I know that this quantity must be equal to the total charge inside. Even if the charge has a shape, which in this case is still symmetric, but it's non-trivial, okay? The electric field here will be related by this equation. And I can use this one to solve for the electric field. So this will be the electric field felt by a test charge that I put near to this central charge. And the force is given just by the value of this charge times the electric field. And with this one, I can really compute for a given distribution of charges, of static charges, which one is the force between these two charges. In this case, then, what we usually do in physics is to define a potential function, okay? which is just a scalar function that is defined everywhere in space, of which, when I take the gradient, I obtain the force. So this result is what is known as Coulomb's law, and it's the, let's say, the basic law of electrostatics. Okay? During our story today, we will see how this law will be corrected by several different kinds of effects. And afterwards, we will also see how the same thing will happen in gravity. And then, also here there is another surface. So, basically, so this is about the magnetic field. Then there is another kind of field that was known still from antiquity, and it's the magnetic field. It was known since when people started to find these pieces of rock which were magnetized, and then it was used for compass, and people discovered that there is a magnetic field on the planet, and the magnetic field is different from the green field, and this is the red field, because basically now the lines of the field are not allowed to have a source, because basically nobody ever saw magnetic monopoles. So now, if we have to represent graphically the magnetic field, it must be something that, given any surface, closest surface in space, every time that the field comes in from one side, it must go out from another side. Okay? So this one is Gauss' law for magnetostatic, and it's the second one of the law describing electromagnetism. At this point, these phenomena were appearing completely different to people, because there is no relation between the green and the red field. Okay? But after the development of the battery, people started having the instruments and the possibility to play around with experiment related with currents. So this black line here is a current. The current is a flow of charges. Okay. In this kind of infographics, when I have a line that comes out from the screen, it's simply something that is like varying in time. It's like if this was my time direction. So you see that the magnetic field is actually generated by a flowing charge, a set of flowing charges. And again, I can use Gauss' law, where I can draw a Gaussian surface here, and I want to measure how's the magnetic field here. Again, I just need to know how long is this path, and it's 2 pi times r, and the magnetic field in this case will follow the line, so will be tangential to these red lines. And this is equal, by the law of Ampere, to basically it's proportional to the current. And the constant of proportionality is this mu0, which is a magnetic constant that people found out it's necessary to introduce. And in this way, you see, you could calculate the magnetic field, and the magnetic field was dropping like 1 over r in this case. And then, once I know the magnetic field and I know the electric field, I can always reconstruct the force acting on a given charge in space. Okay. And then, still in the 19th century, people started playing around with currents, and many people, and one of these I think was Ørsted, so was a Danish guy, they started realizing that magnetic field and electric field are related to each other. At the beginning, this was a very strange phenomenon, because they started realizing that if they had a magnet, and if they were moving a magnet, this will create a current inside the wire. Okay? And soon after, Faraday in England worked a lot about it. He made a lot of experiments, and basically came down to propose the law of induction. So he was able to find a quantitative relation between varying magnetic field and the creation of electric field. Okay? And soon after, Maxwell not only found a mathematical theory to describe this, what came to be known as Faraday law. So Maxwell was able to draw this picture, which basically tells you that the circulation of the electric field is proportional to the variation of the magnetic field. Okay? And then Maxwell also understood that he had to correct the law of Ampere, which we were using in the previous slide, where we knew that the varying charge, so a current, was generating a circulation of the magnetic field. He also understood that you had to add in this equation also this green line coming out from the paper, because, and this was called the displacement current, to have the equation to be consistent. So basically Maxwell was able to, based on consistency argument, to improve the law of pair. And so he wrote down these two equations that together with the previous two equations, which are like this one with the surface, and then this one here, okay, which is just generalized. So this one here, which tells you that the flux of a magnetic field is 0 on a closed surface. He was able to write down these two equations. And so these equations were written down by Maxwell, which is usually here, something like that. And this was 1865 or something like that. And now that he wrote down these two equations, which obviously you can start to see that there is a kind of relation between them, because if I go in vacuum space, you see that I have a varying magnetic field generates an electrical field, and a varying electrical field generates a magnetic field. So then he was in a position to make one of the most amazing discoveries ever made in science. Because then he started asking himself, but what if this line here, I bend it and close it and use again this equation? So when I do this, he was able to find out this equation, which is the wave equation. He basically understood that if I'm in vacuum space, and I have an electrical field, and I have a varying magnetic field, the varying magnetic field will grow in one direction, and at the same time, so since these two circles have different arrows, it means that one field grows, the other one shrinks. And so he understood that in flat space and empty space, in every position, there could be a solution to his equation, which were traveling waves, okay? Traveling waves of magnetic radiation, of electromagnetic radiation. And then he made, the amazing thing is that actually these traveling waves that comes out are actually waves of light. Because basically these two constants that were defined in completely different contexts. So one was defined by Coulomb, studying charges. The other one was defined by Ampere, studying currents. And in principle had nothing to do with the speed of light, were actually related. So this was really an amazing moment because he made the unification by changing the equation. And he had a set of equations that then he could understand that they were predicting a new phenomenon. And so basically, with his unification, Maxwell not only created what is known as modern electrodynamics, but he also understood that light and electromagnetic phenomena are two sides of the same thing. Okay? And this is an amazing case of numerology. Somebody will have discovered this before. And also this one was the end of classical physics, if you want, and the beginning of modern physics. Because now you have the speed of light, and the speed of light is a finite quantity. And the electromagnetic phenomena is really an oscillatory phenomena. But the fact that the speed of light is a finite quantity started changing things. Because now, yes?
Ulo Römer was the one who discovered that light is finite.
That this value is finite, okay? Yeah. Who measured that even before? So people knew that. And then when Maxwell discovered that electromagnetic waves were actually waves, they had to have finite value of the speed, and they came out to be exactly the same number, basically. But now this opened a new, so ended classical physics and opened modern physics, because since you have a finite speed, there starts to be a problem, because so light always go at that speed. It doesn't matter on which reference frame the light source is. So if I have this laser, I'm pointing like this, so light is going at that speed, and also now light is going at that speed. So that started making people think and making people realize that classical physics was somehow inconsistent. And in fact, the fact that, so basically the end point was that the only really relativistic or special relativistic theory we had was classical mechanics. And in fact, this one immediately led to what is called special relativity. Okay, so there are two axes here also. And this led Einstein at the end in 1905 to understand physically what other people understood mathematically before him. That basically light is the top speed, and that nothing can propagate in space faster than light. And this implies that time and space are intertwined to each other, and we cannot consider time as an absolute quantity like we were doing since the time of Newton. Okay, and so this is what developed special relativity, and special relativity was rewriting of classical mechanics to be consistent with electromagnetism. So basically it was Maxwell against Newton, and the judge in this case was Einstein. He said, Newton is wrong, Maxwell is right, I rewrite the part of physics that Newton wrote down that time. And so now we are in, and so basically the outcome of all this analysis is this very famous relation, okay? And this is very important because it tells you that the energy of something, for example, of a body, in a rest frame in this case, is proportional to the mass. So not only this explains or tells you that you can convert mass in energy and vice versa, but also tells you that basically mass and momentum are two sides of the same quantity, which is energy momentum. Okay, and so there is not mass, there is not momentum, there is a combination of them when you speak about special relativity. And then people started drawing diagrams like this one, so people started speaking about space-time, where you have light cones, and when our electrons, so our currents, they are allowed to go only inside the cone here, because the ratio between time and space must be smaller than the speed of light. So basically particles are allowed to propagate only inside this cone, but they cannot go outside. And okay, now, so this was at the beginning of the century. Now to do the next step, we need another kind of ingredient. We need to ask ourselves, okay, but we have seen that there are these solutions which are electromagnetic waves, and we have seen that the electromagnetic waves are light, and we have seen that light goes at the speed of light, okay? But now we need to ask ourselves, what is producing these electromagnetic waves, okay? Because maybe they are a solution of the equation, but there is no way to produce them. Okay, so maybe they're not physical. They are physical because it's the first thing we observe when we are small, probably light after sound. And so the question is, how are, let's say, electromagnetic waves produced? And they must be produced by matter. They must be produced by electron, by something movement. So one idea is that, so to understand what we really need to have, which property of matter generates the wave, we can just go back to the small calculation we made before, and just for a moment try to think that our charge is in motion. So the charge at the same time will be the source of the electric field, but then will also be the source of the magnetic field. Okay? And since in this kind of situation, okay, I can compute my electric and magnetic field using the relation that we saw just before. And in both cases, I find that the electric and the magnetic field drop like 1 over r squared. Okay? So it means that if in my picture of before I said that light is a kind of multiplication, combination of in the same point of an electric field and a magnetic field. So light somehow is proportional to the square of these two quantities. So somehow the thing that we want to call radiation made by a charge which is moving on a straight line will be something that falls off like this. But now if I ask myself, okay, now I know that, for example, I see light coming from stars. Okay? And so something needed to produce light at the star. And it's very far away. Okay? So it means that if matter is able to produce light, I must be able to observe this one very far away, okay? Because I'm very far away from the stars. So for example, if I have an electron or any other charged particle very far away, the radiation that they make, when I go and see the value it has, for example, on a big sphere at a certain distance, this one must be something that doesn't go to zero, because otherwise, at some point, the radiation produced by this moving charge will just dump down, okay? But if I do the analysis with this just number here, I see that the light produced by a charge which is moving on a straight line is something that falls off with the inverse of the square. So we'll never be able to reach it. And this is also understandable from the point of view of relativity, because I can always try to stay in a frame where there is only an electric field because my charge is fixed, and so the electric field will fall down with this power here. Okay. So this means that if I have matter which is just moving straight, I will not be able to produce radiation. And in fact, then the amazing thing is that to produce radiation, you just need to have a charge that bends. Okay? And it's only in the moment in which you have a charge which accelerates that these charges are able to create radiation. So basically, all the radiation that we observe is made by some charge at one point decided to bend. Okay, and this is, if you want, the first hint that we are going in direction of having of understanding light also in terms of particles, because if I have a charged particle that comes and then it bends, it must change momenta. Okay, and so where is the difference in momenta going? The difference in momenta going has to be inside light, which we can start thinking as a new particle, for example, a photon. Okay, and so this is one of the most important things that come out from electromagnetism. That all the light that we see, all the radiation that we see, is generated by charges that bend. Okay, and for example, I don't know. In any case, when you have like for example, this is the, once people understood this opened really a huge, let's say, succession also of important applications, because people start understanding, okay, I need to just have current that change, and this will create waves. For example, this was used by Marconi to create the first kind of communication through space. Okay, because they understood that, okay, if I have a signal, I can just transform my signal in a varying current. The varying current, since my electrons inside are accelerating, they will be able to radiate. And since radiation is like the one that we see from stars, it will be able to travel so far away. And this, for example, are very important things. They came out from an understanding of this. So now, this is a kind of equation that we will use in the next steps in infographical form. I just want to give you the mathematical form that stays under that one. So here is exactly what I mean when I draw this graphic here. Okay, this is the physics, is all the thing I just described to you, but if I have to be a little bit more precise, I will have to write down an equation like this one, which is very interesting because it's, first of all, a very nice achievement to be able to write an explicit formula that tells you how are the electric and magnetic field of an arbitrary charge moving around. But what I wanted to show you is that this first term, which is the static electric field, because you see, just imagine that the speed is very small with respect to c, okay, which is the speed of light. This term will go down, and I will just have 1 over r squared. This is my limit that we understood with Gauss' law before. And this goes like 1 over r squared. What I wanted to show you is that an analytical computation really shows you that something that goes like 1 over r, that then will be able to propagate, because then E goes like 1 over r, this goes like 1 over r, so the product goes like 1 over r squared, multiplied by a surface, which is r squared, goes like a constant. So radiation, so what generates photons afterwards, it's really generated by acceleration. Okay? So, but now we go back to the infographic. So this was an important thing because it was really a real understanding. And then, obviously, this one is already embedded in special relativity, because now we know that a particle propagates, and then at one point it will radiate a photon, okay, and then it will bend, okay. And if we start, if we go on like this, this is really a relativistic theory of matter and photons, if you want. And here we are at the time of like 1905. Then there is another amazing breakthrough, which is the discovery of quantum mechanics. And I will not go too much in detail here in quantum mechanics, but I will, so let me go. So this is the synthesis. Now we have basically understood all classical electrodynamics. It's a theory of photon and electrons. So there is photons which are non-interactive with themselves, they just propagate in free space. And then there are electrons which basically radiate photons when they want. But now, the world is much more complicated. And so basically, here I want to introduce you quantum mechanics directly within quantum electrodynamics, because otherwise we have to take another big parenthesis and we don't have time. Basically, this was what it was known before the discovery that photons or particles, that there is a duality between matter and waves, and that there are Schrödinger equation in place of classical equations. So while we saw that these two infographics, so these two diagrams, that then in the 50s or almost in the 60s, Feynman finally found a very consistent and simple way to think about quantum phenomena, to think about fields in together with quantum. What we basically understood is that together with the classical equation, we have to add other equations that are with other contributions which are purely quantum, okay? And in these contributions, we have to account for the fact that since within quantum mechanics we have the uncertainty principle, and there is a non-zero probability that for a short amount of time we are able to borrow from the vacuum some energy. And this energy can be used to create pairs of particles and antiparticles. So one of the things that we discovered with quantum mechanics that I try to draw with this diagram here is that there are not only any more electrons, but there are also anti-electrons. And for example, there are processes where a photon comes and then splits, and from nothing you see an electron and a positron come out from nothing. And the fact that is that this kind of process, which is a real process, can also happen for a very short amount of time in a very tiny region of space, creating what are known more as virtual processes, which basically give you new Feynman diagrams that correct your phenomena. So light now is not anymore propagating in free space, but it's propagating in free space and creating, for example, in this case, electron and anti-electrons, and going on propagating. And there are even strange thing happen, like for example, a photon is interacting with a photon. While before photon were always being considered free particles, at the quantum level they are actually interacting. Okay, so basically, quantum mechanics is understanding that the world is much more complex, and that there are many more phenomena that you have to consider, and that even a simple theory like classical electrodynamics has to be dressed by all these kind of phenomena. For example, we saw before Coulomb's interaction, okay? And Coulomb interaction now, after Feynman, can be understood in a very simple way, because it could be understood, since now we have both of these diagrams. Let's say before we had only the one of the radiation. Now we can imagine that an electron is coming, at one point it radiates a photon, okay? And then there is another electron that comes, absorbs that photon, and then bends. So we could really start seeing that those forces that before were understood by far away interaction, long, let's say interaction at distant points, like the one in classical electrodynamics. I had an electron here and another electron here, for example, and they were just interacting far away. Now we understand that what is actually happening can be described by the fact that they are exchanging some other particles, like a photon. But then so this is a reinterpretation of the classical result, if you want. But then there are other corrections which are purely quantum, because they have one circle. So the difference between quantum and classical is that a quantum has a circle, and then possible many other interactions. Okay, and for example, one phenomena that it's very interesting of quantum electrodynamics is called vacuum polarization. So the fact that before vacuum was just vacuum, but now you can have that. So the light, the photon that occupying the vacuum, can in any point generate a pair of electron and anti-electron, and since they are charged particles, no, and they are like, they have a plus and they have a minus, they are actually creating an electric field in the middle. Okay, so this is saying that at the quantum level, so if now I can have also this diagram and I can play to put them together, even empty space is not anymore empty, but it's, for example, the electric medium of electron and positrons, dipoles. And this has a very interesting effect on, for example, on charges. Because now, given a charge in empty space, so the charge we started with at the beginning, the one that Coulomb was studying, the fact is that if now I go and look at this charge very near, okay, at energy which are sufficiently, so at distances which are sufficiently small, that there is enough I can borrow from the quantum mechanical point of view, I can borrow enough energy to create an electron and anti-electron, okay? At those tiny scales, I will see that my charge here is surrounded by clouds of dipoles. And what is actually a cloud of dipoles doing is screening the charge. Okay? So it means that the value of the charge, if this is my electric charge will depend on the distance to which I probe it. Okay? And so basically at the classical level I just have something like this. And this is basically the order of the inverse of the mass of the electron, because here I don't have enough energy that I can borrow from, at those long distances I cannot borrow enough energy from empty space to create a pair. But at the scale of 1 over m, I start being in a situation where I can start borrowing some energy to create these pairs. So I will start seeing a polarization cloud around. And this one, and so I will start penetrating it, and then basically this shows you that at smaller and smaller scale, the electric charge will be bigger than I see at a bigger scale. So this really, and then this is a very deep thing that has also been observed experimentally, which is the concept of running charges. So the concept is that what we were thinking was a true constant of nature, like the electric charge, is not actually so, but it's something that depends on the resolution to which I observe the phenomena. Okay? And this is the key ingredient for what later will be called effective theory that we will use. And it's really one of the reasons why we are able to write down models that work. So basically, there are a lot of, oh no, sorry, I can't see it too much. So, this is one of the main points of this talk. So now you have to imagine that we have a grid here. This is our space. Can you see the grid? At least there is a grid. And so let me redraw the picture. So imagine, for example, this process here, which is the process in which light scatters by light. Okay. So as we said, this is a phenomenon which is related to quantum mechanics. So basically, this is a photon that comes, and then there is enough energy to borrow from the vacuum for a short enough time, so that I can create two particles, for example, and then after. So this particle, since it's a particle which I borrow from the bank of energy, after a while I have to give back my credit. So it means that this particle cannot propagate more than a small distance. And this small distance is more or less 1 over m, which m is the mass of that particle. So it means that if I am observing physical phenomena, so now I use this line to, like, let me draw over here. Yeah. Okay. So if I have these two particles and I have a resolution, okay, this is more or less 1 over m, which is enough to see this detail, what I will actually see when I go inside with my big microscope is that a photon is arriving, is creating 2 electrons. The electron then are going in this direction. They will again irradiate the photon and go in the other direction. So they will have a complex quantum mechanical problem. And so I will describe this phenomenon as this process. But if now I look just as a lower resolution, because my eyes are not good enough to see, the only thing that I will see is something like this. So I will see these photons arriving and just interacting. Okay? So somehow this is a quantum theory because I have a loop, I have a closed path, while this is a classical theory. So what the example of the running charge and this kind of reasoning tells us is that at the end, to describe even the quantum phenomena, so to describe even phenomena at very small scale, I can always use a classical theory, so something which doesn't have a closed loop, but has simply a more complex interaction. Okay? So basically, nowadays, which after 70 years we know quantum mechanics and electrodynamics, we understand that the dreams of Maxwell, for example, or of Einstein, that electrodynamics was a fundamental theory of nature. They were wrong, basically. And that we are actually just having something that we call an effective theory. So we are just having enough symmetry and enough consistency conditions, which are imposed by symmetry, and we know enough the properties of the particles that we are able to predict some properties of the energy we are able to observe, basically independently of the details of how the world is at energy much bigger. Because now this argument can be run several times. Now imagine I zoom even more. How many things will explode here? I will never be able to see everything up to arbitrary scale. If I zoom, there will always, everything new will come out. I will never be able to describe it. It's not even, let's say, anymore some irrational way of thinking that there will be an ultimate theory, a multiple simple mathematical model that will be able to predict everything, like a superset of Maxwell equations. Okay? What I will have will always be an effective description. But the very important point is that I'm able to predict, so to say that there is this phenomenon with this number in front, even if I don't know all the details, because basically the details on different scale will completely decouple with each other. So this is basically the concept of effective theory. And in fact, quantum electrodynamics, which is at the same time probably the best, a theory has the best agreement between experiment and theoretical value computed, is actually just an effective theory. We know that if we try to zoom inside more and more, a lot of new interaction will come out that will simply render our calculation not consistent anymore. So we even know that it's not possible with the set of theories, with this set of theory make it with the black line and yellow line to go to greater and greater detail. And so this is basically our understanding of gravity, of electromagnetism. Now we start going with the other force of nature that we want to discuss, which is gravity. So gravity has been discovered much before electrodynamics, but the fundamental law was written down by Newton, and it's basically the same one of, it's just a complete analogy of the one that we have for electrodynamics. So we have that now mass is the source of gravitational interaction. We have only one sign, we don't have charges, there is only one side, so it's an neutral theory from that point of view. And it's characterized by one constant which tells you how intense is the interaction, okay? So now the force is given by this relation, which comes down from a potential like this, okay? So now, to make a story short, we can just go through all the steps we did for electrodynamics. So we have the analogous of the electric field, and there is even an analogous of a magnetic field, okay? But what comes out is that a theory with this electric field and the analogous magnetic field is not a relativistic invariant, so it's not the full story, okay? So, but in any case, you can start discussing about gravitational waves, so gravitational radiation, okay? And you can write down an equation like this one. Now the difference is that it's not anymore enough to have just an accelerating charge to have gravitational waves, which here are blue, okay? And blue is just the graviton, so the analogous of the photon. We can easily do the analogy and construct all these concepts. And the first thing we understand is that it's not enough to have an accelerating charge. So now we need to have two accelerating charges, which are doing something which is not properly spherical symmetric. And this is physically, we have to say that there is a quadrupole. And for example, the first gravitational waves have been found in 73, I think, or 74, by studying a very interesting system of neutron stars rotating one against the other one. These are very massive objects, okay? And when they rotate, they are actually irradiating energy. And since they are waves, which is bringing away energy, and this was possible to be observed because since they rotate, they irradiate, and their orbit is changing, and it will be shrinking. Okay, so at one point they will even collapse because they are basically giving away slowly all their energy with waves. So basically, we could just try to go on and do exactly what we did for the electromagnetic theory. So we have basically the propagation of gravitons in this case, which goes in place of the propagation of photons, and we have an interaction between matter and gravitons, okay? And now we know that we need a more complex, this vertex, if you want, is not enough to generate a wave, you need a more complex situation. But now comes the first big difference that we have between electromagnetism and gravity, which is a very crucial difference, is that since the source of gravity is mass, and now if we want to make it a gravitational theory which is consistent with special relativity, we know that mass is also energy. Okay? But now if we have a wave which is propagating, okay, the wave will carry some energy. So at the same time, the wave will interact with herself. So the crucial difference is that gravity is a self-interacting theory, while electromagnetism was not, was just a free theory. So this tells us that already at the classical level, even before speaking about quantum mechanics, there is not only these two equations, if you want, describing gravity, but we also have to consider this one, and we have to consider this one. And at the same time, the interaction between matter and gravity is much more complicated. We have to introduce this one, and introduce this one. Okay, so it's a very complicated thing because my final theory is not anymore just the yellow line and this one, but it has all these terms, and these terms are incredibly complicated to write down if you want. So it seems basically that it's very difficult to construct a consistent theory of gravity because you have to perform this kind of sum, and this is really an amazing sum, and but it's amazing, but it's possible to perform it. And this incredible sum was made for the first time by Deser also in '73. And the outcome, he summed all these terms, and he found out that the result is curvature. And then he summed all these terms, and he found out that the result is energy momentum. Now I will explain what's the meaning of these two things. But the amazing thing is that you can really perform this sum, and this sum is more or less, it's almost a geometric sum, okay? Even if Deser used a trick to make this sum, but you can actually perform it because this is a kind of geometric sum, exactly like the one of when you sum 1/2 plus 1/4 plus 1/8 plus 1/16. It seems that it's impossible to perform that sum. This was what Zeno was trying to do. And at that time, he didn't have the mathematical techniques to perform the sum and see that the result was 1.
So what are you summing? What are these diagrams?
This diagram I show you. This is just the interaction between gravitons. So this is. So my infographic is blue line is the graviton and the yellow line is the photon. So this is an interaction between gravitons with respect to special relativity that we have already introduced, and everything happens in flat Minkowski space. Okay. So, but now if you write down the equations, this equation here on one side you will have that there is the energy momentum tensor. Okay. And so this one will call you that there are self-interaction that you have to account for. So basically, when you do this sum, you find out curvature, because what comes out from this thing is that the theory is trying to tell you, look, I am more than I'm a theory of geometry. So if you try to make a consistent version of me on a flat space, I will do everything to force you to reorganize all the terms in a way in which, okay, you just have to put aside the fact that you're working on flat space and make a curved space. If you do that, the equation becomes extremely simple. And it's just curvature is equal to energy momentum. And in fact, these are the equation that Einstein found, okay? And this is the shape of the equation, okay? Which is this is the left-hand side is the result of summing all these terms, and the right-hand side is the result of summing all these terms, okay? This equation was written down by Einstein without doing that sum, because it was so difficult that nobody arrived for the first time at this equation by just doing simply the sum that you in principle should do if you somehow logically want to construct a theory of propagating gravitational waves, okay? And it was derived in this way only 60 years after, okay? Einstein found this directly by thinking in terms of curvature and thinking about geometry. And basically, the curvature here is what we call the Ricci curvature is equal to the energy momentum. So basically, this is telling you the mass and energy is bending space, okay? In a way which is proportional to this one. But now let's go on following this kind of reasoning. So now if you want to do a quantum theory of gravity, at this point it's very simple, because we just need to add also the diagrams with 1h bar, okay? So since we had this kind of diagram in the classical theory, we immediately also have this kind of diagrams. And then we have all these kind of processes. For example, we have gravitons that are interacting not only by themselves, but these gravitons are also interacting by just creating these kind of pictures. Okay, so this is basically quantum gravity, and as it stands, it's a theory which is consistent also with quantum mechanics and with special relativity, because we just constructed it that way. The only real problem and the only real difference with the other quantum theory is that these equations are extremely complicated. And just to give you an example of how this infographic is synthetic, this diagram here, it's, let me just see one thing first. The nice thing about quantum gravity is that it's a theory with 3 fundamental constants, because we have a quantum mechanical constant, which is Planck constant, the speed of light, which is the constant coming from special relativity, and Newton's constant, which comes from that. So a real quantum gravitational phenomena will have a prediction which will be a combination of these numbers, will contain these numbers, okay? And the real reason why, the common knowledge is that we don't have a theory of gravity or we are not able to quantize gravity. It's mainly due to the fact that this theory is very complicated. Because, for example, if you take this diagram, this vertex here or diagram here, and I just wanted to write down, it's still another one. So now that I have my theory of quantum gravity, I can see which are the correction, for example, to Newton's law. Okay? Because Newton's law is the classical theory, is the non-relativistic theory. Then there will be correction from the fact that I summed over all the classical interactions. And then there will be correction coming from the quantum interaction. And for example, I can just compute this correction by just evaluating these contributions. So I'll have a particle coming, okay, and the particle is exchanging a wave of gravity and then go on. But at the same time, I can have a particle coming, change a wave, but then since the wave interacts with herself, she can create another couple of virtual gravitons and so on. And to be able to compute the correction to Newtonian interaction, I need to consider, for example, this set of diagrams. I can just write them down, and then I just perform the calculation and I find the result. The reason why this kind of things took so much time, and for example, the first consistent calculation of the correction to Newton's interaction came only in '94, is that they are very complicated. Because, for example, this simple thing that I draw here is actually representing this thing here. Okay? So, and conceptually is not different from electrodynamics. It's just algebraically a nightmare, if you want. Because gravitational waves are more complex, so they demand this kind of interaction. So now, just imagine when I have a diagram like this one. So we have seen how is this vertex. So here you have to have this thing here times this thing here times this one and times this one. So you have to multiply this. You have to multiply this times at least square.
There's a minus sign.
Yeah, no, there is. I know. I already wrote to the. Just to say. So imagine multiplying this thing. So then you will have. If these are 100 or 100 terms, the multiplication will have 1,000 or even more. And it's simply very complicated. So this is the real truth behind Feynman diagrams. I mean, they're very simple and they give you the result in 5 minutes. But then sometimes to just write the solution, the result in a different form, you have to perform a lot of computation. But in any case, we can do it, okay? And so we were saying that we want to find the correction to Newton's interaction. So this is Newton interaction. Now we want to write a theory which has just a potential modified by all these effects, which I can use like my effective potential to describe the phenomena. And we can write down the correction to Newton's potential in this way. And it's very simple to understand why we can write them down in this way, because this is the classical result. So we take it outside and we put a 1. And then we know we have now, you're doing quantum gravity. So we have 3 constants. And now we can just look at combination of these constants so that they have dimension of meter to some power, and then we will divide that combination by the relative power of R. For example, first of all, we can realize that if we just take G times C squared, so G times C squared divided by C squared, so we have S squared kicks away this one. Then we have M squared under, so we just have M over. And then we put a mass here which kills this one. We just have something like 1. We just have something as the dimensionality of R. So if we divide this combination by R, and then by symmetry we make the sum, we obtain that there should be a correction like this one. And since in calculating this correction we didn't use this is just a general relativistic correction. So this is a correction that comes out from a diagram like this where we don't have loop. So this is a correction that comes down from the first amazing sum that we did. And in fact, this is a correction from general relativity. And there is so just on
so quantum mechanics has nothing to do with this correction yet, right?
With this one, no. It's with this one.
Okay.
So this one is the general relativistic correction, the first one, okay? And there is a number that then we can compute. It will come out from the diagram. I can compute it using general relativity in the standard way, but I can just compute it with a diagram. The diagram already will have also this correction inside. But then there is another combination which I wrote down here that you can just check that comes out correctly, that gives me something that goes like 1 over R squared, okay? And so this is the first genuine quantum gravitational correction to the potential. And so, just on arguments about dimensionality, I know that I can parameterize my effective vertex here. Will have the form like this. So now what I just need to do is just to compute the diagram. So A comes out from this diagram here. So basically 1 and A will come out from this one. B comes out from all of these ones, okay? And they are all like this, but somebody did it, and they found this result. So 3 here and 41 over 10 pi, okay? And this actually was made in '94 for the first time. They didn't got immediately the right number. It took 10 years, 5 different groups to agree which one is the right number, because everybody was spotting mistakes in the calculation of the other one. Because, as you said, one group had this minus sign wrong, and another one had this one, for example. You know? And that's how it went. And so basically, this is where I wanted to bring you with this story. This is one of the most amazing results we have in gravity, and it's actually the first unambiguous result that we have about quantum gravity. So we know which one are the corrections to Newton's potential between two charges at the level of h bar. This is a completely finite result? Yes.
Yeah, so in QED, for example, there is a finite, there are 3 diagrams basically that diverge, right? That you have to sort of like fix by renormalization.
Yes.
From what I know, gravity, the number is infinite, right?
Yes, absolutely.
Okay. So how do you know how to normalize the theory?
Yes, because this is
in order to claim that this result makes sense. To get
absolutely, because this is the effective field theory result, which is basically this. Every time I integrate the theory, okay, in an effective field theory approach, there will be some number, there will be some contribution to the effective action that are completely not sensible to the UV completion of the theory. Whatever is my UV completion, this kind of result are independent of those. Okay, so they are genuine result that every possible theory of gravity that will be well defined at a very high energy, in that limit must reproduce. And there is a specific way to spot, and this is exactly the analogous of what you do in, for example, in chiral perturbation theory. There are the chiral logs, the numbers in front of there, that are simply dictated by symmetry, and they are completely finite. So even if chiral perturbation theory is not renormalizable as a theory, and even if we did a new QCD, in any case we were able to compute those numbers, and those numbers will, for example, will go inside the pion amplitude, and we were able to predict that amplitude without knowing about QCD and with a non-renormalizable theory. This is exactly the same thing. We are using a theory of an effective theory of gravitons, okay? We don't know the analogous of QCD, but in any case, we're able to compute some contribution to the interaction, the leading contribution, okay? If I go to the next contribution...
So sorry, so all these diagrams that would have been disarmed by Diesel, those wouldn't be effective?
No, the Diesel is just a way to obtain the classical Einstein's equation. It's not, the work of Diesel was just finding waves, finding general relativity starting from gravitons, interacting with each other. It was just a way to arrive to classical gravity.
So this
when you talk about quantum gravity, you talk about an effective
version of gravity, yes. Like I do when I speak about electrodynamics, like I do when I speak about chiral perturbation theory.
So this correction is valid for large R, right?
Yeah, this correction is at the low energies.
So large
yes,
R.
Absolutely.
Okay.
Large R's, and we can even... Because the point is that you will also have local corrections proportional to delta functions, and the coefficient of those numbers are dependent on your renormalization. So to fix those, you need an additional experiment, okay? But the low energy, so the powers of 1 over R, they are completely set and defined by the symmetries and the principle of quantum and special relativity, exactly like here, simply without doing all the details of the computation. So for those who know chiral perturbation theory and chiral logs, this is exactly the same thing. We just computed the pion scattering, and we know that we don't need to know anything about QCD, and we know that that number will come out finite. We did exactly the same thing. And so this is a genuine calculation in quantum gravity, and it's even so good that the correction is so small that it's not observable. And that's the only problem with this kind of calculation is that, because if we now try to put the numbers, and so this is the first term, the general relativity. So now let's go a moment next to the sun here, okay? And we see how big are these corrections. So we find that the correction from general relativity is 10 to the minus 6. The quantum correction is 10 to the minus 8, okay? So it's extremely small. So obviously we can, this formula here will never be possible to find an experiment where to test it. But the important thing is really, this formula is telling you another thing, that classical relativity is such a good approximation for so many order of magnitude, because it's, it's showing you really that in a full computation you can compute something, and this something first of all is finite, and it's even small, which even tells you that your approximation is even more justified. But this is really obviously giving you again which one is the scale of gravitational interaction. It's really telling you that before observing gravitational correction, general relativity is a perfect effective field theory. So basically, if you want, this number here is a derivation of Einstein's equations. Because just imagine you don't know anything, you just use the principle of quantum mechanics and special relativity. You will write down all possible diagrams, all possible effective terms. How to decide which one I have to keep? I have to compute the correction, and then I say, okay, the two dominant terms are so dominant that I can use them basically everywhere. So the reason why the person that did this calculation didn't get the Nobel Prize, because the number that came out is too small to be observed, and nobody will ever observe it, okay? But this doesn't mean that we will not be able to see quantum gravity effects, because exactly the same kind of reasoning that we applied here, the one of effective field theory, can be applied to other situations, for example, to the whole cosmos in certain moment of its evolution. And probably there, we can see some real correction predicted by gravity. And probably 2 weeks ago, we had the first news of a measurement that can be able to somehow go and probe quantum gravitational effect. Because also when you do the theory of the quantized perturbation in the background, what you're doing is considering an effective theory of gravitons, in this case the Friedman-Robertson-Walker metric, not the flat one like we did here, for example. And there you're using the dominant term given by the algorithm on effective field theory to quantize the tensor perturbation, which are basically quantization of the graviton. So if there is a place where in the future we will probably be able to test the theory of gravity, is the cosmological one. That's it. Any question?
So, do you have any activity for the second quantum correction? I mean, so
the first, there is only one quantum. Yeah, the second one.
I know, but how do you know that the second one is not of the same order of magnitude? How do you take care of?
Yeah, because there is a, it will be g squared. So it's very easy. Yeah. So, yeah.
But that doesn't depend on the UV theory, or?
No, probably the next one will depend on the U theory.
So,
because it's only sum of, yeah. But because in expansion inverses.
I mean, by dimensional arguments, I understand.
No, but I mean, I think that it's really.
But it means that the coefficient is very.
Yeah, no, in fact, the only thing that it can be is that in a calculation like that one that was performed here, the only surprise you could really have if you find a coefficient which is order of magnitude big or small, so that it really changes the argument, but is order unity. So you really see that it's a very simple correction. But if you just live in a world with a different value of G or H value, it would just be an effect like the vacuum polarization. It's exactly the same kind of phenomenon, or the running of the charge. Simply, it's too small to be seen. But the point is that the status is that quantum gravity is exactly the same, has exactly the same status of quantum electrodynamics, which is the best. The theory has the best agreement between experiments and theory. So it's not, even if it's true, quantum gravity is not normalizable in the perturbative sense, which tells you that there is, if you apply that particular technique, that particular action, you will need to renormalize more than a coupling, order by order.
So, from the size of these corrections, shall one conclude that there's actually no need in looking for a finite realization of gravity?
Yeah, I mean, yes.
So should I just be happy with classical general relativity?
Yeah, if we didn't have like the CMB, yes. If we didn't have the cosmic microwave background or that kind of observation, yes. But now the news is that it seems that gravity is quantized because the tensor modes are so big and they are really quantum version of them. But you have to go at the time of inflation, so 10 to the 16 at least,
Okay.
GeV.
What about more, what you might call exotic objects like black holes or even possible naked singularities?
If you do the calculation for the big astrophysical black holes, it's still a super tiny effect. And yeah.
No, you should look actually at small black holes. And you'll see an effect.
Yeah, but then as small black holes at one point will break down. You cannot,
you see the correction depends only on R, so you just need to go to R small enough.
Yes.
Compared to M of R and the other.
Okay, Alessandro, let me understand something. So the second term, okay, there is no H bar there, so that means this is a person coming from general relativity.
This is just general relativity.
Okay, but people were able to get this term by doing this scattering with gravitons, you say?
Yes.
And they found the coefficient 3? I mean,
Yes. This one is the one that you find from post-Newtonian approximation if you start from general relativity, or from...
I know that you can find it from general relativity. I'm asking if you can find it from
for sure.
the Feynman diagram.
Yeah, it's just the first time that comes out from the Feynman diagram.
Okay.
So it's just the one where you drop the polarization. It's just coming out from the fact that the propagator in gravity has two indices, and it must be metric minus metric with alter 2 combination.
So how come it doesn't depend on H bar then?
Because it's the 3 level. It's the 3 level, and so that's. Because that's the reason why I wanted to propose you general relativity starting from waves, because really, I can. I mean, even if we were not able to do that sum and nobody knew Riemannian geometry, we were able to find this correction to explain the precession of Mercury and a lot of other things. I mean,
how did you pick your Feynman rules for calculating that 3?
The 3, yeah, it's just.
Did it come from an Einstein Lagrangian?
Yes, they come from the Einstein Lagrangian.
Ah, okay.
Yeah, for sure.
Yeah, okay.
For sure, they obviously.
Yeah.
But then why does
so trigger you get them so.
Yeah, then
So then it's sort of a trigger statement that we get the correction, right?
No, yes, it's.
What did you do post? Exactly, yeah.
But I can, yes, but what I say is that I can, yeah.
Yeah, it's a classical.
It's exactly the classical,
So what do you do
nothing.
with Feynman diagram? So what do you do with Newtonian?
Yes, it's exactly the same thing.
Exactly the same.
If I use Feynman diagrams at the 3 level, I just wanted to say that I could do Feynman diagram without knowing R, without being able to use Riemannian geometry to write everything in a covariant form. Just by using the 3 vertex that I obtain by consistency, in which I start from writing down the wave equation for spin 2. By consistency, I get the next term, which will be proportional to free h mu nu. Okay, so I have the linearized equation. So the wave equation for the graviton is something that it's a linear equation for h. So as an action, which is h squared. Then I use consistency to find the one with h to the 3rd power. Okay. And even easier, I use consistency to find which one is the interaction here. And then I just compute the Feynman diagram and I already get that correction. Without the need of realizing that there is geometry. It's completely a quantum, let's say, field theoretical argument.
Why does the last term then not depend on the UV theory still?
Because it's the log. It's basically the log Q in your diagram, exactly like the chiral log. That one will not depend.
The next order it will.
The next order it will.
The next order in H, yes, the G square contribution, yes.
So at what scale does it break down? This description breaks down.
So the expanding scale is the Planck 1 over the Planck mass. So it's it's if you reason like in Kira perturbation theory, you have the pi and the k constant. That's your scale. So at what scale will it break down? It's the same question. So if you know how to answer in Kira perturbation theory, you can do it also here.
And the symmetries that determine that coefficient?
The symmetries is just invariance under diffeomorphism.
Okay, yeah.
Yes.
So just invariance under diffeomorphism determines that.
So it's a gauge theory with that. And they completely fix that coefficient without knowing the UV completion of gravity. So that's a real prediction. That's a point. And it's if you want, the first real prediction that we have in quantum gravitational phenomena, which is.
And when was this? Sorry,
94.
94.
Yes. It was inspired by Weinberg, and then Donoghue is the same guy of the book, Dynamics of the Standard Model. He did the computation, and the only problem is that it's complicated. So he did it, and he found that number wrong. I mean, he had a number. And then it took 10 years, and now it's only in 2006 that they all agree that that's the value. Because people just you lose pieces. And so this is just you saying that somehow gravity is complicated just because you have this kind of relations. So you know, in a 2AD this is 0. That's it. But if you, in fact, let me say another thing that is interesting. This diagram here, has been computed in '95 by Dunbar and other people using those new techniques like the helicity techniques where you write gravitational scattering amplitudes at the square of Young-Mills. Okay, so this string-inspired technique that now people is also, and the same technique is the one that they are using now in supergravity to calculate the divergences. So they basically write gravity theory, they make cuts, and then you can relate art to an interaction in Young-Mills and so on. But for example, if we have to see what is known here, this one is known in an expansion. So this one is known basically completely. This one, yes, also. And this one, just a part of it. So people compute it. They just compute it without using it in an application. But if you then extract the low energy, the logs of those terms, all of those are like some low energy corrections, which are independent of the UV completion. So that's. So I would say this is the status of quantum gravity based on the principle of effect of field theory.
These diagrams have been estimated like in sort of like flat space. So the final diagram that people calculated were like in flat space. I mean.
Yes, depending on what you can calculate, you can use covariant techniques where you never specify a background and compute the effective action as a functional of the metric, which is the most general one. And this is, but for example, and when you do that, then you have an effective action that you can apply also to different backgrounds. So you can do effective field theory on Friedman-Robertson-Walker, for example. No? While this calculation was made with a flat background to simplify, because only in flat background this is so simple. and so they were able to compute the Newtonian potential in flat space. But if you want to compute another, you cannot covariantize that result so easily, even if you can try. But the point is that even if, so now it's true that the scale of inflation is 10 to the 16, which is 1,000 times smaller than the Planck scale. It means that also the gravity in principle can be treated like an effective theory, most probably. So even probably for all the cosmological things that we will observe, we can still use gravity like this one. And probably, because then if you want to discuss more generally, we always live in the broken phase of gravity where the metric has an expectation value which is non-zero. So probably all the physical questions related that contain G, that contain the free constant here can be addressed within effective theory, within ever, because probably there is. So okay, that's it.
So you said in this article introduction about light scattering.
Yes.
So Hilbrook scattering, right?
Huh?
Hilbrook scattering, I think it's called, right?
Yeah, I don't know exactly.
Yeah, but has that actually been observed directly?
I don't think so.
Yeah, so light by light scattering.
It's not yet observed.
Directly has not been observed.
Yeah, I think so.
Yeah.
I think so.
Which is quite.
Yeah, no, I was exactly.
It's quite funny, a QED thing.
Yeah. It has not been.
It's a box.
Yeah.
Yeah, exactly.
Yeah, that's actually what I refer to. That diagram is the Euler-Heisenberg-Lagrangian,
Yeah.
which is the two terms with f to the fourth power that you can write, and they are known since 37 or something.
So then what?
The diagrams that I meant there, it's like the Euler-Heisenberg-Lagrangian, which is f to the fourth power, no?
Yeah.
Which is also there. This is a low energy prediction that you can compute, and it's known since a lot of time. And then the other one that I was actually considering was the Uru effect, no, the Wu-Helding potential, basically, where you correct with the log and then makes the charge run and so on.
Which potential?
Wu-Helding effect? Yeah, they are. Like, it's the first effect of.
I mean, light by light scattering contributes to the knowledge of it more. It's being computed with fiber, graph.
But I think people claim they're not observed directly.
Probably not. But
this is not a direct.
if you compare
Yeah,
the experiment and theory form, I don't know, when in the moment of the moment you need the alpha to the 4 and alpha to the 5, which includes the light by light scattering.
Why do they claim that? I think they do.
But I mean, that's not the same as observing.
Yeah. Observing.
That would be like using a laser experiment.
Exactly. Yeah. But I think we haven't done that.
It wasn't anything done.
I don't think so.
I think we haven't done that. Right. Any further questions? Thanks again, Alessandro.